Okay, before I begin with what I actually want to talk about today, I have to apologize. I said something wrong last time and I want to make a correction. So, Bailenson-Soulet does not already imply that we have Motivic Lie algebra. So, if we have Bailenson-Soulet, we get a Abelian category of mixed state motives, but and we get a functor from the derived category of this Abelian category to the triangulated category of mixed state motives. But this is, I mean, it does not formally follow from Bailenson-Soulet vanishing that this is an equivalence. So we know that this is an equivalence in the cases where we know Bailenson-Soulet. That was why I was getting confused a bit. So we know this is an equivalence in the number field case. And function fields over for a curve over a finite field, and so any case where we actually know the Bailenson-Soulet vanishing conjecture, we also know that this is an equivalence. But it.
Why you have bounded?
Well, it depends on what your definition of mixed state motives is. Okay, so that was that. The other thing, yeah, so I mean, this means then that the existence of a Motivic Lie algebra which computes the graded pieces of K-theory is yet another conjecture a bit stronger than Bailenson-Soulet. So we got that right now. And the other thing, the freeness of the Lie algebra, I think, is a theorem of Francis Brown in the case of mixed state motives over the integers. And I guess, but I have not really much of knowledge about this number theoretic situations. I guess that some motivation for expecting freeness of this part of the Motivic Lie algebra could be in expectations about the transcendence of periods. Okay, so what have I done so far? I explained a bit what Motivic cohomology is, gave the definition of Bloch's higher tau groups. And last time I explained a couple of the conjectures, a couple of their relations, and how we sort of assume that everything is as good as it could possibly be. We get complexes computing the gamma graded pieces of K-theory or Motivic cohomology with rational coefficients in terms of some more or less explicit complexes. Let me write down these complexes more precisely in weight 2 and weight 3. So in weight 2, this complex is, there should be some kind of Bloch group for the field. And there's, I mean, the complex just has length 2. It maps to the second exterior power of the units of the field. And then that's it. Right? So this should compute the weight 2 part. So this means that the co-kernel here should be Milnor K2, all the fields with rational coefficients. And the kernel here should be K3 indecomposable of the field. So this is what comes out of the conjectures. Weight 3 case then looks, we have some Bloch group B3. Then we go to field tensor Bloch group B2 of the field, go to third exterior power of the units. I mean, all suitably rationalized, you know. And then this should compute the corresponding pieces of K-theory so that you have a cohomology group here, Milnor K3. Then here the weight 3 part of K4 and here the weight 3 part of K5. So this is what the conjectures would predict. So what I've explained you so far. And now what I want to talk about today is group cohomology, or group homology. Well, sorry. So let's leave a bit the shaky ground of all these conjectures about Motivic cohomology. And it seems from the lectures earlier today that this is a great day for explicit computations.
F star, we don't tensor with Q there, right?
This should all be tensored with Q.
We all tensor with Q.
Yeah, I'm only trying to make rational statements at this point. So, yeah. Right, what I want to explain today in this section on group homology is how complexes of this form, something like this and something like this, come out of computations for group homology. And well, historically, I suppose such a complex was written down I guess end of 70s, beginning of the 80s. Bloch and Suslin later wrote down this complex, and I guess this is one of the historical starting points. So this being able to write down a complex like this, which computes the appropriate pieces of K2, the appropriate weight 2 cases of K-theory, came before actually being able to formulate more general conjectures what things should be like. Okay, so right, so I want to talk about group homology. So the computations for group homology that I'll give you are non-conjectural. You can really do these computations and then you get a result. The link to Motivic cohomology is conjectural. So, so I'd first like to sketch how you would possibly link group homology to Motivic cohomology and what the relevant conjectures there would be, and then go through the computation of the homology of SL or GL2, which gives rise to this complex, so that you actually in particular also see an explicit presentation for this relevant block group B2 and see where the relations come from and so on. Okay, so I said in earlier parts of the lecture, possibly several times, that statements for Motivic cohomology over general schemes can sometimes be reduced to statements over fields. And yeah, also we understand the finite coefficient cases much better than we understand the rational cases. So for most parts here, I'll be interested in looking at the situation. So this is related to via conjectures to Motivic cohomology with rational coefficients of a field with rational coefficients. Right? So this concerns the field case and rational coefficients, and some of the statements do not generalize beyond this case. But I mean, this is sufficiently interesting because already the K-theory of the complex numbers is yet unknown. So over fields, we can compute K-theory in terms of group homology, and it works like follows. So the higher K-theory you can give a definition. This doesn't quite work. Well, okay. So you can give a definition of the higher K-theory as, well, we take the infinite general linear group, if we're more specific, over a field whose name shall be F. We can look at the infinite general linear group, GL of F, which is an increasing union of the GLNs. then look at the classifying space BGL of F. This has fundamental group GL of F, and then there is the Quillen plus construction, which is sort of the universal thing that kills the maximal perfect subgroup, which we know is the subgroup generated by elementary matrices in there. So we kill this, make pi1 abelian, such that the homology doesn't change. All right, so this is a construction. This does not change the homology, but it drastically changes the homotopy. The homotopy becomes interesting then, and so you can look at the ith homotopy group of BGL F plus and define Ki of F like this. So, of course, this works for a ring as well, but we're interested in fields here. So we have this. The other thing is that because we're using rational coefficients, we generally have the Hurewicz map that goes from the homotopy of a space, for instance, BGLF plus, to the homology of that space. So now at this point, it doesn't actually matter if I write plus or omit plus, because the plus construction doesn't change the homology, right? So we generally have the Hurewicz morphism that goes from homotopy to homology, induced sort of by making a simplicial set into a simplicial abelian group. And this map exists in general if I take now rational coefficients. Then because the BGL F plus is an infinite loop space, so BGL F plus is an infinite loop space, so then you get additional structures, namely this becomes a graded Hopf algebra. Right, you always have something on cohomology. You have the cup product, and that gives you the same thing. The diagonal gives you a co-product on here, and this infinite loop space multiplication gives you a product. And then, so what Cartan-Serre theorem tells you is that this map, the Hurewicz morphism tensor Q, is the inclusion of the primitive elements. Right, so you have this Hopf algebra, and then you have the Lie algebra of primitive elements in there. So you can compute, I mean, so in general it's more complicated, the relation between homotopy and homology, but in this case, if we're looking at the space BGL F plus, it becomes much simpler, such that in particular we can, I mean, so these things would be the rational K groups. We can in principle obtain them from homology. If we know this structure of multiplication given by the infinite loop space structure, we then can figure out what the primitive elements are.
But isn't it an isomorphism? And the inclusion rationally?
Yeah, it's an inclusion. So this Hopf algebra would be the universal enveloping algebra of this Lie algebra, and so it can generally be larger. Yeah. Yeah, so that's basically what I wanted to say. With this. In principle, we can compute a rational K-theory from group homology. And let me point out at this stage that essentially all the cases where we know some conjecture like Baylis and Soulé vanishing, like a finite field case, number field case, and function field of a curve of a finite field, they all basically go back to group homology computations and then deduce some K-theory results from there. Okay, so I mean this is only a very vague statement here. In principle, we can compute K-theory from group homology. So let me make some more precise statements. So I want to discuss the rank filtration and the rank conjecture, which should give an explicit, well, explicit. This is what I mean when I say conjecturally statements about group homology can be related to Motivic cohomology. This refers to this rank conjecture that I want to explain. Okay, so there is a definition of the rank filtration. So how does this go? Probably I want to reduce to infinite fields here. But that's not really such an essential point. So on the K group Kn of f with rational coefficients. Right, so I mean the point is we have this, where the K groups embed into the homology of the group GL, and GL of f has a filtration by the GLNs. So for the homology we can ask, does such a homology class come from GLN, or does it come from GL2, GL3, or whatever GLN does it come from? And this filtration of the homology in terms of from what rank does the corresponding element come from induces a filtration on K-theory. And that's the rank filtration. All right, so the rank less or equal m part of Kn of f tensor Q is given by, well, we want to intersect K-theory, Kn of fq, with something on homology, namely we have the subspace, the image of the map Hn of GLM of fq goes to Hn of GL of f with Q coefficients. Right? So we take those elements in K-theory whose image in homology comes from GLM. This is the rank filtration. It's an increasing filtration, of course. And I mean the map here is really just functoriality, right? You have a map from GLM to GL because GL is defined as the increasing union of the GLMs, and then you have the functoriality for homology. So you get an increasing filtration, and we can say something more specific about this. Slane stability results tell us something about this filtration, namely the rank less or equal n part of Kn of f is Kn of f. Right, so everything in Kn already comes from GLN, and the first subquotient, so rank less or equal n modulo rank less or equal n minus 1. So I'm omitting the Kn of f here for laziness. This is exactly Milnor Kn.
You said this is for finite fields,
Infinite fields.
Infinite.
So it's not really interesting for finite fields, but so technical reason. Yeah.
So what you confuse is for.
Yeah, sorry. Yes, so this is some filtration on K groups. We already saw another filtration on K groups. Right, so we have, let me write it like this. We can write down a filtration of K groups. I mean, the gamma filtration. I already mentioned that. And in the terminology that I wait. So yeah, and the graded pieces of the gamma filtration are denoted like this: K and J of f. In the whatever I. So let me say it like this. gamma kn of fq, and of course this is show j of fn tensor q. This is a sort of direct sum decomposition of kn, and then we get a decreasing filtration. I guess there we can say f greater or equal m with index gamma, because it's gamma filtration, kn of f q, and then you take the direct sum of j from j equals m to n, and then you have kn j of f. Right. So this is another filtration.
Yes.
Yeah.
How is the second result? Is it coming from stability? The fact that this n-1 is made on KTV?
This is a part of Suslin's stability results. I mean, the one result says in, if you look at homology hi gln with I less than n, you get isomorphisms, and then you get an exact sequence, namely from gln minus 1 to gln, and the co-kernel is explicitly identified as Milnor kn. Right, so we have two filtrations, one coming from group homology, the other coming, well, from Motivic cohomology. We can say like this, and there is the conjecture concerning the relation of these two things. Well, and this is the rank conjecture. It essentially says that the rank filtration splits the gamma filtration. So basically rank less or equal n kn of f q plus f greater or equal m plus 1 gamma kn of f q is equal to kn of f q. Right, so you have one increasing filtration, one decreasing filtration, and then so you get decompositions of the K theory in terms of these spaces of the two filtrations. It's a direct sum. Yeah. Any more questions? Yeah.
Stability results are two integral.
The stability results are integral statements, yes.
And is there an integral conjecture this form?
I would doubt that. I mean, this is, I mean, the gamma filtration is something that you would only want to define. Yeah, maybe. So, I mean, for, I'm not sure if there are integral statements about this. Yeah. I guess you certainly get issues with the direct sum decomposition at this point, and probably, I mean, I guess the torsion in group homology and in Motivic cohomology should probably be rather different. So I'm not so sure about integral statements at this point. So one remark is that this is known for, again, the standard cases, so for number fields. This is Borel and Yang. Well, it's also known for function fields for curves over finite fields, but again, in the higher K theory is rationally trivial, so this is not really a statement anyway. So this is known for number fields, and well, the relevant consequence is, I mean, in the definition of Motivic cohomology, we're not really interested in the filtration, I mean, but we're interested in the graded pieces. And the thing is, if we know the rank conjecture, this is essentially what you get from this, the graded pieces for the gamma filtration and the graded pieces for the rank filtration are basically the same things. Right? So they're isomorphic, or you want to say this. right? So this in particular means that if we take rational coefficients and we have the rank conjecture and we want to compute Motivic cohomology with rational coefficients, you can also look at what are the rank graded pieces of K-theory and compute those in terms of group homology. So this is one of the reasons why this would be a very interesting conjecture to know, because homology computations are easier than homotopy computations, so you may expect that it may be easier to compute group homology, even if it's of general linear groups, than to compute K-theory. Right, so so the consequence here, let me see it again. So in principle, so with rational coefficients, Motivic cohomology could be computed via group homology if we know this conjecture. Let me write it explicitly. So hi of f qn, that would be cho n of f 2n minus I. This is the appropriate graded, the nth gamma graded piece of k2n minus I of f. And then assuming the rank conjecture, this would be the nth graded piece of the rank filtration of k2n minus I. So this in particular means if the rank conjecture is true, then Motivic cohomology comes from GLN and the corresponding 2n minus I homology group of GLN in this case. Yeah?
I can define another filtration which is not the intersection of the stable K-theory with the image of the homomorphic homology, but the image on the plus construction from BGLN M plus to GLN to GL plus. Is it a different filtration?
Possibly yes. I mean, I'm not quite sure. So at least in the stable case, we know that BGL plus is a loop space and all that, and sort of in some sense we're also using that we can embed the K-theory there as primitive elements of homology, and it's not a loop space on the finite stages, so I'm not sure about that. Could be possible, but I don't know. Okay, so, right, in principle, Motivic cohomology of weight n should come from GLN. And so let me now discuss the special case rank 2. Right, so what can we say about the homology of GL2 or SL2, PGL2? There's not much difference between these groups. So yeah, that's basically the question here. How can we understand homology of, well, some of the relevant groups here? I mean, GL, the general linear group, is the thing that gives rise to K-theory, but you know the difference here is only in the units, and this is sort of this is K1, we're dealing with the higher K groups, so there's not much difference if we're interested in the higher K groups, we could also look at BSL of F plus. So, yeah. So how can we understand the homology of these groups? I'll focus on rational homology computations, but some integral statements are possible. And so what I want to talk about is, as I said earlier, due to Bloch and Suslin, so yeah, but I'd like to take this opportunity to point out that in particular Z1/2 integral homology computations for SL2 have been done by Kevin Hutchinson. So and while these results of Bloch and Suslin pertain to Motivic cohomology, I guess the computations of Kevin Hutchinson and the Z1/2 integral stuff in SL2, this gives rise to refined Bloch groups with quadratic information. So that may actually have something to do with Milnor-Witt Motivic cohomology. Possibly. Okay, so for simplicity, and because the complex numbers is already the most interesting case to look at, I'll assume that F is quadratically closed. In that case in particular, there's no difference really between SL2 and PGL2. And that simplifies a couple of things later. But again, stronger and more general statements are always possible. So how can we now compute? So I'll now look at the homology of SL2, right? How can we compute the homology of SL2 of F? F is a quadratically closed field. We're interested in rational coefficients. How do we do this? Like you do, well, how do you do computations for homology? You use injective resolutions to prove all sorts of general formalism. But if you want to do concrete computations, you have to choose nice and easy resolutions. So particularly those coming from geometric situations. So what we can do is look at SL2 of F, and there's one most natural action, namely the one on, so SL2 acts on P1, and then we can act with SL2F on the F points of P1. Right, so this is just the action of the group on the set, so this is nothing that we could use to compute cohomology, but we can make this into a complex. Namely, we get the chain complex. Let me write this as C star P1 of F. So in degree n, this, so Cn of P1 of F is the free abelian group generated by n plus 1 tuples of points. In P1 of F. Right, so you take n plus 1 tuples of points in P1 of F. Now this is why I mentioned this restriction, for infinite fields. Right, quadratically closed also implies infinite. What can we say about this complex? This complex is acyclic. So it has no homology because you can actually write down an explicit contraction. The basic geometric input, or the basic input there is if you have a cycle in degree n, this is n plus 1 tuples of points, but this involves only finitely many n plus 1 tuples, so only finitely many points. You can always choose one more point. And so because you have this freedom to always pick some point that you haven't used before, you can actually write down explicit contractions for this complex.
Sorry, what is the differential of this complex?
Sorry?
What is the differential of this complex?
Ah, sorry, yes. Thank you for pointing that out. The differential is the one that take a0 to an, and that maps to the sum of -1 to the I, and then you omit ai. So then that's take alternating sum of omits one after the other point, and that is the differential. Right. Yeah, so it's basically a check complex associated to the set P1 of F, and then yeah. This is going to be a cyclic, and then therefore this implies that you get a spectral sequence. Right? You can compute the homology of SL2 acting on this complex in terms of a hyperhomology spectral sequence that goes from the homology of SL2 of F with coefficients, let me write it like this, CP, in CQ of P1 of F. Right, in the qth group of that complex, take the pth homology. This is going to be the E1 page. And it converges to the homology of this complex, well, to the homology of SL2 with coefficients in this complex. But because this is a cyclic, this is really just the homology of SL2 with coefficients. Right, because I wanted to, sorry. Free abelian group or Q vector space. Now, depending on what coefficients we're talking about, right? So if I take the complex with rational coefficients, because this is a cyclic, homology of SL2 with coefficients in this complex will just be homology of SL2 with Q coefficients. So we get some additional structure on the homology of SL2 by writing down a geometric resolution of the constant thing in terms of the action on P1. And the point is now this spectral sequence can be used to deduce sort of a complex computing the rank 2 pieces of group homology. So let's look at this spectral sequence. What do we have? So let me draw the chart. So P is the homological index, and Q is the thing depending on how many points are we looking at. And so what we have in the 0th line here would come from C0. So here we have HP of SL2, C0. Next line would be HP of SL2 of C1, HP of SL2, C2, and so on, right? Then we need to make some identifications. Right? What happens in the lower rows? right, HP, there's something called the Shapiro Lemma. And it's basically, well, what do we have here? We have HP of SL2, C0 would really just be the free abelian group on points in P1. So we have a transitive action of SL2 of F, sorry, on P1 of F. Right? Every point can be moved to infinity. And then the stabilizer for this transitive action is going to be the group of upper triangular matrices. So Shapiro's lemma then tells you this group of SL2 with action on this free abelian group of 4P1 of F is the homology of I'll write Borel subgroup. And let me not abbreviate this to B. So the homology in this row here, if you take it with SL2 with coefficients, you can reduce it to just the homology of the upper triangular matrices with constant coefficients. And then here you can take Z or Q. Right? So that's the next row. What do we have? C1, we're talking about 2 points in P1. And you can always remove the degenerate configurations here. So you can deal with the, cross 2. You can always deal with the degenerate configurations by a different argument, but then the relevant point is if you have two different points. The action of SL2 is still too transitive, and you can move the 2 points to 0 and infinity. And then the stabilizer is going to be the diagonal matrices. So again, you find that this homology group is the homology of the diagonal matrices. Well, but there we can just write actually F star with Z coefficients.
So now we consider only all, no, not all tuples of a point, but points in general position.
Yes. And then in the next case, and this is also where we would like to use quadratically closed, and here we'll look at the homology with coefficients in C2. This means 3 points. Again, we remove the degenerate configurations by some other argument. And if we have 3 points, we can still move them to 0, 1, and infinity. And then for the further things, we don't have enough transitivity anymore. 3 points, so if we have n points in general position, we can move the first 3 to 0, 1, infinity, and then it stays like this, because the stabilizer of 0, 1, infinity in SL2 would be trivial. Sorry, the action, the stabilizer would just be the diagonal matrices plus minus 1.
You were saying that when you try to compute this homology group course with coefficient in CQ for Q higher than 1, you're saying you can assume that all the points are distinct or something?
Yes. Yeah. You can. Maybe I can reformulate this. I mean, you can also write down a quasi-isomorphic complex, which consists only of points in general position. Maybe I should have done that in the first place. Sorry. Okay. So we have this. And then we have basically for Q greater or equal to, when basically the points in general position have at most finite stabilizer, we can say that the Pth homology of SL2 with CQ coefficients, this is going to be when you take the group ring of SL2 to the Q minus 2 for I equals 0. Maybe I'm missing something here. I think I want P1 to the Q minus 2. And then there's some 2 torsion. Sorry, for P odd and 0 for P even. So what I wanted to say is that this spectral sequence, the E1 page, simplifies quite a bit. So in here, the 0th row, we would have the homology of the upper triangular matrices, which, because we have an infinite field, we can get rid of the unipotent part, and so this would exactly be the homology of the units also. So here we would have, this is the homology of F star with Z or Q coefficients. This is the homology of F star with Z coefficients. And then from there on, basically what we have in, so on the Q line, we have points. So here we would have Z, just a Z, because this is Q minus 2 is 0. And then if we go further up, here we would have points on P1. And here we would have P1 of F times 2. Right? Everything else in this spectral sequence is not really interesting. There appear some 2 torsion groups at some points, but that's really not so essential. The interesting information is in those 2 rows here and the column. And then you can work out what the E2 page is. All right, so what do we have? 0, 1, 2, 3. For Q, we have 0, 1, 2, 3 for P. And we have integer here, 0, exterior power of F of the units. We have a Q mod Z here, just to indicate what could happen with if you're not using torsion coefficients. So there's a 0 here, and then there's a group that I call PC, PF at this point. Right, so I mean the homology of F star, because this is an abelian group, there are explicit formulas, and essentially you can, you can write this down. There are explicit formulas for the homology of abelian groups that you can use. So these 2 lines are not so essential. You have to work out what the what the differential does here, but that's not so problematic. And the interesting thing that appears is then at this stage. Let's try to understand what happens here. And I wrote it here. We have at this point the free abelian group generated by points in P1, and here above the free abelian group generated by 2 points in P1. And so you can work out, I mean this is also implicit here. Here you have a Z, and here you also have a Z, and this map actually is an isomorphism, and so that you get the 2 zeros here. So this means that P of F, let me write this here, PF is given as the co-kernel of, well, it's H0 SL2 on C4 mapping to H0 SL2 C3, and we've written this over there as this. Here you have 2 points mapping to one point. So a free abelian group. Right, so how does this identification go actually at this point, right? What can we say? We have H0 SL2 of F with C3 coefficients. So we're talking about the SL2 action on 4 ordered points in P1. And we want to map to ZP1 of F, right? How do we do this? So I mean, what we have here is, here we have 4 ordered points in P1, and then we take co-invariants for the SL2 action, so orbits, essentially, right? So again, if we assume we're working with a complex with where we do not use a degenerate configuration, so we have points in general position. So we have these 4 points, and we want to map it to 1. The obvious thing to do is you can use the SL2 action to move the first 3 points to 0, 1, and infinity. Right, so in here you have a representative for this tuple as 0, 1, infinity, and then some other number, some other element of F. And then of course you map this to this element Z. This is classically, so Z is the cross ratio given by A0 minus A2 over A0 minus A3 times A1 minus A3 over A1 minus A2. This is the unique invariant for an ordered tuple of 4 points in P1. Right, so this is this identification that we have here. If we're looking at this map up here, then we're just saying, okay, here we have 5 points, and we map to 4 points by saying, do I still have it? Yes. Take the alternating sum. You have 5 points, you have 5 summons, and then you have 5 possibilities to omit a point, and this alternating sum is going to be the element that you get in H0. So this is what you want to divide out. Now, if you translate this to this presentation, right? So move all the points to 0, 1, infinity, and whenever you get some other tuple, again, use the SL2 action to move the first points to 0, 1, infinity. Then this easy differential that we had here translates into something more complicated. But of course, much nicer and more interesting than the obvious relation, just omit all the points in the order and take the alternating sum. Right, what you get is, I wrote D. D translates into a 5-term relation, right? So if we take this obvious differential and then transform it under this cross ratio thing to ZP1 of F, we get the following presentation. PF is the free abelian group generated by those elements Z in curly brackets. Z should be from F without 0, 1, because we don't want the points 0, 1, infinity. They're already taken by the first 3 points in the cross ratio formula. And you divide out the following relations. I have Z1 minus Z2 plus Z2 over Z1 minus 1 minus Z2 over 1 minus Z1 plus 1 minus Z2 to the minus 1 over 1 minus Z1 to the minus 1. And here, well, index set is you take Z1 different from Z2, and they should both be from 0, from F minus 0, 1. Right, so this relation appears, or comes out of this differential by taking cross ratio invariance. And then the thing is, well, the differentials in the E1 page went like this. The differential on the E2 page is now going to go like this. Nothing happens there. And then there's the next differential on the E3 page. And we get an exact sequence. So we get H3 of SL2F. If we're working with integral coefficients, there would be a term coming from the roots of unity there, but that's torsion. Then we have this P of F there. Then we go to lambda square F star. And then we go to H2 of SL2 of F. It goes to 0, and you can actually identify this map here. It sends Z to Z which 1 minus Z. So that you basically see the co-kernel here is going to be Milnor K2, but we knew that from Matsumoto's theorem anyway. And then, so up to, with rational coefficients, this here can actually be identified with K3 indecomposable of the field. So there is something more that you need to say at this point, because what we have computed now is obviously homology of SL2. And that this has something to do with K3 indecomposable. You still need to make some more arguments to say this bit actually survives to after stabilization, right? You go to SL3, SL4, and to SL infinity. That this thing survives and actually gives you exactly K3 indecomposable is yet another argument, right? But basically, that's what I wanted to say. Here we get a complex of length 2, and that's really a computation. This is not nothing conjectural. You get a complex of length 2, which has roughly the form that I indicated at the beginning of the talk. It computes the weight 2 pieces of K-theory, right? Here you get Milnor K-theory, and here you get K3 indecomposable. Right, let me mention some terminology. These things all have names. Yes, I'm writing the terminology here. So this PF is sometimes called pre-block group. Some people prefer scissors congruence group, because this is what we'll see tomorrow, that over the complex numbers, this is actually related to scissors congruences in the 3-sphere and in 3-dimensional hyperbolic space. And then the kernel of this map from PF to lambda 2 F star, you can also call this B of F. This is the block group. Right, so let me mention, there is a similar story, slightly more involved.
This kernel.
Yes. But note that I'm using, this is because we're using rational coefficients here. So there are more general integral statements where you would have something here as well coming from H3 of the units. So this is basically essentially from roots of unity and so on. So in general, the K3 indecomposable, if you're looking at integral coefficients, is a bit bigger. It has a Q mod Z in there that you would also detect with finite coefficients. And the quotient modulo this Q mod Z would be the block group. Right, so let me mention that there's a similar story for rank 3. You can actually take the action of, say, SL3 or PGL3 on the projective plane and work through the corresponding spectral sequence. This has been done by Dupont and Sa. And then you get a complex like the weight 3 complex I mentioned at the beginning. in which the relevant piece computing the weight 3 part of K5 is given in terms of configurations of 6 points on the projective plane. And in this situation, again, you have this cross ratio thing. And if you then use this cross ratio to translate the obvious relations coming out of this complex here, well, you have the similar complex for P2, then this obvious relation turns into a functional equation for the trilogarithm. And this is one of the things behind Goncharov's proof of the Zagier conjecture for zeta of 3. So to wrap this up and say something at the very end here. Right, so what we have now is a complex computing weight 2 Motivic cohomology. So we have Milnor K2 and K3 indecomposable. You can do more with this. Namely, you can look at analytic questions. Again, yeah, I didn't talk about regulators and so on, because this would make the series much longer. But if you already know what the regulators are, then I'm telling you that what you have there is 5-term relation This is essentially the functional equation, or it's related to the functional equation for the dilogarithm function. Let me say the complex version of this would be Li of 2, and given by the power series start with n equal 1 to infinity z to the n over n squared. And because you have this functional equation, so there's a real valued version of this that satisfies this functional equation, and that therefore gives you a function on this p of f. And then it's possible to identify this dilogarithm function on this block group with the regulator on K3 indecomposable. And then to end this, I mean, you can give very general sort of explanations of zeta values in terms of, what appears here in this complex. So this is work of Zagier. And I can't resist, I have to write it. So you have this. Zeta of 2 is pi square over 6, but it's actually also the dilogarithm. So there's actually no reason at all to bring this up now. But so as you can see, the zeta of 2, you sum 1 over n square, is the same thing as plugging in 1 into this dilogarithm function. And so what Zagier did was you can actually then identify so zeta values at 2 for number fields in terms of the regulator defined on the block group, and then express zeta values at 2 as dilogarithms evaluated at particular elements in the block group. And so this gives more precise formulas for, a priori the regulator on K-theory is defined in complicated ways, and here this is maybe slightly easier. Here you're talking about configurations, cross ratios of configurations of 4 points, and you take the corresponding evaluated dilogarithm there. So I mean, what I wanted to say is that this complex is also useful in number theoretic contexts to provide vast generalizations of this fundamental theorem. And so conjecturally there would be higher dimensional generalizations, and as I said, so this, the story for the weight 3 complex with PGL3, this is one of the inputs for Goncharov's proof of Zagier's conjecture for zeta of 3, which again expresses zeta of 3 in terms of determinants of trilogarithms evaluated at suitable elements in things coming actually from these group homology computations. Okay, so much for now. This should wrap up what I wanted to say about the relation between group homology and Motivic cohomology, and tomorrow I'll say something about the relation to scissors congruences. Sorry for the overtime.
what about vanishing in wave 2? If you can do this computation, can you do vanishing? What's the obstruction? Where are you?
So, I mean, you can continue the analysis of this sequence. And this expresses the higher homology groups for SL2. And you can basically say some stuff, I mean, you get an exact sequence for the homology of SL2. And the other two pieces are, on the one hand, you have the homology of the normalizer. But this is the stuff that comes in here. This is decomposable stuff from units. And so this is not really so relevant for the higher K-theory. And the other stuff would be groups of configurations of points, just more points on P1. And well, I guess you can analyze and you can ask how much of this stuff well, yeah, I mean, what is missing for vanishing is now you need to understand how much of this higher homology actually persists and survives to SL infinity. And well, if you don't have the rank conjecture, I mean, if you had the rank conjecture, this would mean that you need to show some vanishing of higher homology groups. But again, the vanishing of higher homology groups here would, you have to analyze configurations of points on P1. So, I mean, there are, I guess, two questions that are basic to getting vanishing out of this formalism, and that's Suslin's rank conjecture. And even if you have that, it remains to analyze configuration, so these groups of configurations of points, which has a tendency to be difficult.
So this rank conjecture is based on the fact that the K-theory injects inside homology group rationality of perfectness.
Yeah.
So is this injection true for more general kind of rings, say local rings or something?
Yes, the injection, I mean, so you only need that K-theory, I mean, that BGL plus is an infinite loop space. And so that's always the case. And you have this operations with the matrices, and, or I mean, you can do all sorts of arguments. BGL plus is the K-theory space, and there are many ways to show that this is an infinite loop space. And if you know that, then you get this injection of the rational homotopy into the homology.
So in that case, why the conjecture is made only for fields? Because I think you can make sense of all the rank filtration and this lemma filtration, and the statement makes sense. So why it is? I'm wondering why it is only for fields.
I think it's, I mean, the behavior of this is different in higher dimensions. And already for, I mean, the stabilization behavior is different. If you look at curves, I mean, like if you look at an elliptic curve, there should be interesting elements already in K1, which doesn't actually happen in these cases. So I have to think a bit about this, but I thought at some point that there are obvious problems, but I can't remember them now, if you want to formulate this over general things, even for curves, with the behavior of the rank filtration.
Okay, anyway, we can continue further discussions at wine and snack reception in 5 minutes, and let us thank the lecturer again.